Assalamu alaikum. Hello everyone, my name is Taibir Jamal. I am assistant professor at Wurla University from Algeria. In this presentation, I will tell you about state feedback control of DC-DC converter using all-clear integral controller and Kalman filter observer. And this research is for the ICDTA 2021. This research belongs to joint research I have with some colleagues from the University of Tbilisi, Galma and Gardaya. The outline of this presentation is listed here. Initially, I will tell you about the introduction of this research, and also later I will describe the modeling of the back boost converter with a negative output voltage. Then the linear quadratic regulator with integral action control is applied for optimal control. Next, the Kalman filter observer is applied for filtering and estimate the output voltage and the inductor current of the back boost converter. And later simulation results and concluding this presentation. Introduction. The electronic circuit designs often require power sources with negative voltage. There are many different ways of producing negative output voltage from a positive input voltage. One option is the simple and low-cost polarity inverting or back boost converter. The advantage of this topology are that it requires low component count and that it can be pulled with standard high side corregulator, such as those intended for back regulators. The focus of this paper is on the autopilot control loop design of DC-DC back boost with negative output voltage. The back boost converter model is chosen among many linear models linearized under various operating conditions. The control methodology used to design the output voltage and the inductance current control are based on linear quadratic regulator with integral action control techniques. For filtering and state estimation with low cost and less complexity, a state observer is obtained based on a Kalman filter observer. A complete back boost converter model is simulated and developed in the MATLAB simulating environment using the SimPower System toolbox. So, modeling of the back boost converter with a negative output voltage. The polarity inverting back boost converter is a very basic power conversion topology like the back or the boost converter or the boost topology. Each of these basic topology is built with one active switch, usually a MOSFET, a diode, and an inductor. Figure 1 shows these three basic voltage conversion topology. The simplicity of the polarity inverting or the back boost is one of its biggest advantage. So, with an inverting back boost, we can create a negative output voltage from a positive DC supply voltage. The absolute value of the negative voltage can be higher or lower than the absolute of the input voltage. Our first step is to model our back boost converter. For most DC-DC converter, we model this converter in three steps. First, model the dynamic state of the system. Second, simplify and linearize the system around the equilibrium point. Third, obtain the transfer function for linearized system. In this presentation, we will just model the dynamic state of our back boost converter. Here is a diagram of the back boost converter. This converter is controlled by the active switch MOSFET 1. When the switch is on, the input voltage is directly connected to the inductor L. This results in accumulating energy in L, inductor L. In this stage, the capacitor supplies energy to the output load. When the switch is off, the inductor is connected to the load and capacitor, so energy is transferred from L to C and R. Compared to the back-boost converter, the topology, the polarity of output voltage is opposite to that of the input in back-boost converter. By applying Kirchhoff's laws in two previous circuits, we get the following dynamics in the switching on and in the switching off. The dynamic of the converter are therefore as follows. In order to control the state variables of the back-boost converter, which usually are the current through the inductor and output voltage across the output capacitor, the control strategy using state feedback control has been applied to allocate the poles of the closed-loop system in any position. An advantage of the Alkier method when compared to the allocation method is that the first one provides systematic mode of calculation for the state feedback control gain matrix. Let's consider a system defined by the following equation. Our objective is to find U such that we minimize the cost function G. We can solve this optimization problem by different methods like dynamic programming or Lagrange multiplier or Hamiltonian. The main steps, without going to play into the details, are: firstly, solve Riccati differential equation, and then the optimal control is with K is. Therefore, optimal control equation is. The block diagram of the Alkier with integral action is shown in this figure and is named specifically as LKI. The Alkier with integral action require the following extended matrix configuration, with K is state feedback vector gain and KE integral action error gain. For filtering and state estimation with low cost and less complexity, a state observer is obtained based on Kalman filter observer. The Kalman filter algorithm is this one showing this picture. It's made by 5 steps. In our paper, we use the Kalman filter for estimation the inductor current and the output voltage of back-boost converter. Here we have a block diagram of open and closed loop control. We used a manual switch to switch between open loop and closed loop control. According to the results of the simulation, the waveform of output voltage and the inductance current have the same characteristics for the open loop and the closed loop control, but the value of output voltage in the closed loop is minus 40 volts and about 37 volts in the open loop, and the current is about 6 ampere and 5.6 ampere in the open loop. The closed loop with Alkier has better dynamics responses compared with open loop. Here we have a block diagram of the Alkier controller with integral action with Kalman filter observer. The algorithm of the Kalman filter was implemented using the continuous time Kalman filter block. In this Kalman block, we can say that the inputs are the measured output voltage and the optimal control U, and the output is the output voltage and the inductor current. This figure shows the real and the estimated inductor current and output voltage when the Kalman filter is used. It can be seen that the signal estimated by the Kalman filter track the real signals and the noise effect is reduced. Conclusion: the main advantage of the state feedback control based Alkier techniques that has a positive effect on response settling time, reducing the undesirable back overshot and serve having less oscillated performance. The simulation results found that adding a Kalman filter reduced the cost and impact of the sensor on healthcare tracking performance. Future work will address the practical implementation of the developed control and adding photovoltaic in this system. And if you have some question, I have been so glad to answer you. Can also contact me through my email. Thank you so much for watching this presentation.